Welcome to lecture 22, in which we're going to introduce a very powerful new concept, that is momentum. So we're going to look at one primary example, and that is a truck and a car crashing into each other. And so in the course of this lecture, we're going to discuss these topics, momentum and momentum conservation, and this is really why momentum is a thing in the first place. We briefly mention the notion of impulse. And we're going to finish with some tips on using momentum in calculations. I will postpone discussing a number of examples to future videos. Let's look at the situation here. We've got a car crash, and imagine maybe it's a big truck and a smaller car, and they're hitting each other, they're coming straight at each other, and they're crashing. Now, the question is, what happens in that crash? Can we analyze this crash? And the answer, of course, it's difficult to do that with the tools that we have, right? It's a big, giant crash, so we want to ask, what happens? What sort of forces might be acting between the truck and the car? There are probably normal forces, they're pushing against each other. There might also be friction as different parts of slide past one another. Parts get bent out of shape, and there might be some elastic bits that want to bounce back. It's a big giant mess, right? The forces will be in different directions, like the dented front of the car and the dented front of the truck. They're going to push against it in all sorts of angles. Like, it's a big giant mess. And we can't really make sense of it. We can't really predict how those cars are going to crash unless we know an awful lot about what exactly this truck looks like on the outside and inside. Same thing about a car. Maybe we do a very detailed, maybe computer simulation to figure out what would happen. But we can't just write down an equation, figure out what happens next. But here's something we do know. We know whatever the forces are, they're going to obey Newton's laws. So let's start with that idea. So what we're going to say is that the force on the truck due to the car, right, that's equal to the force on the car due to the truck. And actually, because that opposite direction by Newton's third law, you put a minus here. Right, so this is true by Newton's third law. If you don't quite remember what that says, and you should, but just pause the video and check that, right? So Newton's third law says the force on the truck due to the car is equal to minus the force on the car due to the truck. Now, let's imagine that this is a very intense interaction. It certainly is, right? And while they crash, other forces aren't really relevant. So the friction with the ground, right at that very instant, that fraction of a second that they're actually crashing into each other, the friction with the ground doesn't matter. Air resistance doesn't really matter. Those forces are tiny compared to the very violent interaction between the car and the truck. Right. So what does that mean? That means this force is essentially the net force up to some very small extra extra additions due to friction and air resistance, say, maybe other forces. Same thing here, right? So for the purposes of this brief violent interaction, this is essentially the only relevant force in each case. So that means I can use Newton's second law, so then by Newton's second law, I can say this becomes the mass of the truck, if I write m truck, you know what I mean, times the acceleration of the truck, then will be minus the mass of the car, right, because the force due to the truck is the only force acting on the car for all practical purposes. All other forces are tiny in comparison. The acceleration of the car. Okay, now what is acceleration? It is technically the time derivative of the velocity, but let's assume that the force, the acceleration, is constant during that short time interval that the interaction occurs. So I can write this as the mass of the truck times the change in velocity of the truck divided by the change in time, the time it takes for the collision. And then I've got minus m, the mass of the car, times the change in velocity of the car divided by the time it takes. Right? I haven't introduced anything new yet. I haven't made any new assumptions. I'm simply using what I know about Newton's laws to talk about those forces, even if I don't exactly know what the forces are. So now I've got those two equal to each other. Now we can assume we know the two masses. And those times, they're of course the same. Right? Because they denote the time of the collision. I mean, in a sense, Newton's third law doesn't only say there's the force in opposite direction equal magnitude, it also says, look, that force, or the combination of forces, acts for the same amount of time, right? When the truck stops pushing on the car stops pushing on the truck. Right? So, that they act for the same amount of time, it's the time of the collision. I might call it the time for the interaction. Whatever type of interaction it is, normal forces, friction, all that stuff. Okay, so that means I can cancel it out, left and right, and I can write very straightforwardly that the mass of the truck times the change in velocity of the truck is equal to minus the mass of the car times the change in velocity of the car. Okay, let's leave it like this for now. I'm going to write something underneath here, so maybe leave a little space, but I'll come back to this. What I want to do first is I want to write delta v simply as v final minus v initial, right? The change in velocity is the difference between the initial and the final velocity of each one of those two. So let's do that. And then let me see if I can write it like this so we can still see the last line. So that implies I get that the mass of the truck times the final velocity of the truck, let me put the F up here because I would write truck down here, minus the initial velocity of the truck is equal to minus the mass of the car times the difference in the velocity of the car, how that has changed over the course of the collision. So I can write that like this. Okay, now we can just multiply this out, and I'm gonna get the mass of the truck times the final velocity of the truck minus the mass of the truck times the initial velocity of the truck. That's equal to, there's a minus sign here, so minus minus, I'm gonna write that first, mk v car initial minus mk v car final. So as I said, those two are the other way around as here because of this minus sign out front. Right, so it's minus minus plus plus vi minus this one v final. Okay, so bit of algebra I suppose, but what's the point? Now let's rearrange this. Let's rearrange it, and I want to bring all the final quantities to the left and all the initial quantities to the right. Right, so I'm just going to rearrange, write this down. I want to get m, the mass of the truck. Now this one I'm going to go take to the right. This one I want to bring to the left. So I'm going to add it because it's minus. Other side becomes plus. V car final. And what do we have on the right hand side? I've got this term, and then I'm going to bring this term over so it becomes positive as well. What am I doing? The mass has changed in this case. V initial truck plus the mass of the car times the initial velocity of the car. Okay. So what is this saying? It's saying multiply the mass by the velocity at the end and add them together for all the components of the system that are interacting here, the truck and the car. That's equal to the same expression, mass times velocity of each one added up before the collision, initially, right? So this suggests that something in this whole process that we don't really understand, this complicated car crash with lots of forces acting, very violent, well, something remains the same, namely this quantity, m times v, so m car v car plus m truck v truck. This quantity as a whole remains unchanged. We say it is conserved. Now, what is this thing that's conserved, this quantity? Well, we call this the total momentum of the system. And we specifically call m times v the momentum of an object. So this would be the momentum of the car, and this here would be the momentum of the truck. Of course, we could have had, two bricks slamming into each other, or any two objects, doesn't matter whether they're cars or trucks, and we've made no assumptions about the velocities either. Right, about initial velocity, we didn't say is it positive or negative, is it big or small. We made no assumptions whatsoever about any of them. Although here I've treated only one-dimensional, right? I've said kind of implicitly assumed it's all along a straight line right now, but we'll generalize that too in a little bit. So this is a very general result. Let's write it down. Momentum is conserved. Let's first define momentum explicitly. The momentum, I'm going to give it a symbol P. Momentum of an object P, and it really is a vector because it has direction, because velocity does. It's mass, the mass of an object times its velocity. Right, I don't know off the top of my head where the symbol P comes from. Why is it P? P does not stand for, it's, the word momentum, but it probably has some historical reason why P has been used. So this is our definition, as it were, of momentum. But note that we're not saying the momentum of the car is conserved, or the momentum of the truck is conserved. What remains unchanged is the total, right? So this is total initial momentum. This is total initial momentum, total final momentum. So let me just sort of put a little star here, and maybe a little, whatever you call this symbol here. Then I can say that star, that quantity here is the total final momentum. So the total momentum is just the sum of all the individual momenta of the objects. Notice that the plural of momentum is momenta, from the Latin. If you ever take a Latin course, momentum, neuter goes to the plural r, with the r ending. Total initial momentum. Right. So the total momentum is conserved, but not the momentum of individual objects. I'm not saying that this is the same as this, that the final momentum of the truck is the same as the initial momentum of the truck. No, nobody's saying that. All we're saying is that the total, that stays the same. Don't know how much of it is here, how much of it is here, or like, are they even both positive? Is one positive or negative? Well, I don't know, but what I do know is that the sum, that is conserved. Let's make this a bold statement, that our total momentum is conserved. The total momentum of a closed system is conserved. This is our statement. Let's annotate this to make sure we understand it. So the total momentum, what do we mean by that? By that we mean the sum of all individual momenta And what do we mean by a closed system? Well, remember in our car crash example, we assumed, or we stated, that all other forces, external forces, are irrelevant. So the friction with the ground in this case, right, didn't matter. Friction with the ground doesn't matter, at least not during the fraction of a second that the crash is actually occurring. Of course, afterwards, the following seconds, as the two vehicles, they slide across the road, hit a tree, well, other forces are relevant. And eventually they probably both come to rest. But during the short interaction, we can ignore other forces. That means our system is closed. So a closed system means there are no external forces acting on the system. Now usually, say in the case of the car crash, this is only approximately true. Like there is friction with the ground even during the half a second that constitutes the actual crash itself. But that force is very small compared to the violent forces of the collision interaction itself. Right, so it's approximately true. Those other forces are very small in comparison. You can kind of throw them by the wayside. But technically speaking, they're there. Right, so total momentum is conserved. In practice, we only often have very good approximation to that kind of scenario. Okay. Now let me briefly come back to introduce another small terminology. Remember, I asked you to leave some space here, because given that we call m times v the momentum, we can now label this as the change in momentum of the truck. And accordingly, this is the change in momentum of the car. So I might call this delta P car, and this delta P, remember P stands for momentum of the truck. Delta change in momentum of the truck, change in momentum of the car. That is assuming the mass stays the same, right? Now we could think of a situation where that's not true, where the mass does not stay the same. But in most of the examples and cases we'll be looking at, the mass of the object doesn't really change. So we'll maybe see one or two counterexamples as well. Right. So how does the quantity m times v change? Well, that is the change in momentum. If the mass is constant, well, then only the velocity changes. Okay. So now let's actually take our example and just plug in some numbers to see what happens. So let's go back to this one here. And I'm going to redraw it for a second, and I'm going to add some numerical values. So here's the same situation, now drawn in the very budget version of my picture. And I want to assume that the truck weighs 3,000 kilograms and the car has a mass of 1,000 kilogram, and that both are going 10 meters per second. Now, because one's going right, one's going left, I actually have to be careful. We're putting a minus sign here, right? At least if to the right is my positive direction, then the car has a negative velocity. And that's important. If I define the to the left as positive, then I should have put a minus sign there. But, you know, it's a choice. It's a choice you can make. The answer, the prediction of what happens next is going to be the same. We're going to suppose the two vehicles, they stick together. They stick together after collision, so they get sort of entangled, they crash, they're hooked onto each other in some way. Which way are they sliding and how fast? That's what we're trying to figure out. So let's use what we've learned. Use momentum conservation. So my initial total momentum is equal to my final total momentum. That is what momentum conservation says. What is the initial total momentum? Well, it's the mass of the truck. I'm going to abbreviate this with T and C now, otherwise I'm going to go mad. V initial of the truck plus the mass of the car times the initial velocity of the car. And that is equal to the mass of the truck times the final velocity of the truck plus the mass of the car times the final velocity of the car. So total momentum is the same before, initially, and after. So those are values that I have, right? I can actually work this out numerically. Let's plug in the numbers. 3,000 kilograms times 10 meters per second plus 1,000 kilograms times minus, and the minus is important, right? It matters which way the car is going before the collision. Minus 10 meters per second. And that's going to be equal to, well, this is going to be 30,000 minus 10,000, so that's 20,000 kilogram meters per second. Notice that this is the unit of momentum, kilogram meter per second. Notice that it's not the same as a Newton. A Newton was a kilogram meter per second squared, right? And funnily enough, this unit doesn't have its own name. A kilogram meter per second squared was called a Newton. And later on we're going to meet the joule. It also has the joule is a name for another sort of combination of kilograms and meters and seconds. But funnily enough, the momentum unit, kilogram meters per second, does not get its own name. Just call it a kilogram meter per second. Now what's it equal to? Well, the value is 20,000. And on the right hand side, we're going to, well, we don't know what these ones are, but we know that it's same, right? We know that it's same because they're sticking together. That was important, right? There are two unknowns here, so we can't really solve one equation for two unknowns, but we're told they stick together, so they must have the same final velocity, or else they couldn't be sticking together. Let's just call it V final without any subscript. That's just one. And so I'm going to get, guess I'm going to put the equal sign here now. The mass of the truck times the final velocity plus the mass of the car times the final velocity. Okay, so that's equal. I can simplify this on that side. Get the mass of the truck plus the mass of the car times the final velocity. What is that? That is 4,000 kilograms, 3,000 plus 1,000, times V final, and now I can solve it, right? 20,000 is equal to this, so I'm going to get that V final, the final velocity, is 20,000 kilogram meters per second divided by 4,000 kilograms. Okay, we see the units work out nicely. Kilogram cancels kilogram. I'm left with meter per second. That's the unit of speed. but 20,000 over 4,000 is just 5 meters per second. Now notice there's no minus sign here. There could have been a minus sign there. Positive, so that implies it's to the right. Because in our coordinate system we started by calling this positive, this negative, so we said to the right is positive. We got an answer that is positive, so that means the final velocity is to the right. Had we chosen a different coordinate system and said this is positive and this is negative, then our final answer would have been minus 5 meters per second, so that's physically speaking the same thing. An object moving to the right at 5 meters per second of speed. Okay, so I hope this made sense, this calculation to you. Notice there were two unknowns, and it happens quite often. And here we had this simplifying assumption that two vehicles stick together, right? We need to know something else other than just momentum conservation to be able to solve for two unknowns. And it could be this, and we'll meet other types of possibilities down the line. If you feel a little bit unsure about this, just pause the video now, go back and see if you can apply momentum conservation to this problem and work through this yourself in your own way. Let's hop back a moment now. We started out using Newton's third law and Newton's second law, right? Those were the only two ingredients that led to momentum conservation. That was it. We have not invented some new physics. We have not hypothesized some new law. We derived a new relationship. We derived the conservation of momentum understanding Newton's second and third law. So here's Newton's second law. Again, of course, this is the net force, but if there's just one, well, it's just whatever force it is. Now, what we said before was m times dv dt is the same as ma, because a is dv dt. Or if I want to be, if I want to do this, infinitesimally with calculus, I'd write dv dt. So I can just take this and I just rearrange it by taking the delta t to the other side. Before we had Newton's third law and we cancelled that out, but if we're just looking at one object, we apply it to Newton's second law and we can rearrange to get f times delta t. That's m times delta v. Now you notice what this quantity is on the right, this here is my change in momentum. This one here we give a name, force times the time during which it acts. We call that the impulse. It's sometimes given the letter J. It's of course a vector because these quantities are vectors and I should have had vectors on here from the start. So the impulse is the force times the time over which it acts. The statement is then that the impulse is equal to change in momentum, but again, this is not something obscure and strange. It's literally just a rearranging of Newton's second law. Like, there's nothing profound here. Now, actually, this is not useful nearly as often as momentum conservation is. And the reason is that the powerful thing about momentum conservation, right, it allowed us to work through all of this stuff here and figure out those 5 meters per second to the right in the end of our example, is that we didn't have to know about what types of forces were acting. We didn't care if it was a crash with violent normal forces, or maybe they were like magnetic cars that sort of repel each other and they only sort of magnetically bumped. We didn't care. We really didn't care. Momentum conservation applied because all forces obey Newton's laws, and that's all we needed. If you want to work with impulse, well, you need to know about the forces again. But sometimes it can be a useful concept. There are some applications where using impulse is really, really useful. But in general, for solving problems, if you use impulse, you could have used Newton's second law, because they are essentially exactly equivalent. Whereas momentum conservation itself gives us new tools to solve a problem that we couldn't have solved with just forces, like that car crash. So that's the basics of, those are the basics of momentum. Now what's left to do for us is really just to do some examples to see some other applications applying the principle of momentum conservation, and also to generalize it to more than one dimension and to work some examples there, because I know from experience it can be a little bit subtle. So we'll do that. I'll do that in the follow-up videos. But in this video, what I'm going to do now is just give you some tips on how to use momentum in calculations, some pointers that might be helpful for you to have. Here you go. So here are some tips on using momentum. Let me go through them. First, to note, the total momentum of a closed system is conserved. That's exactly what we said, of course, and not the momentum of a single object. I'm emphasizing this because often enough I've seen the mistake made that you say, oh, momentum is conserved, momentum of the car is conserved. Not true. You have to take into account all the different objects and their momentum. Sum them up. Only the total is what is conserved. And if you've got external forces acting, like something is pushing from the outside, well, then either you can't use momentum conservation or you have to include the effect of the external force by either including whatever is doing the pushing from the outside in your momentum, or by having a total momentum change by the impulse that that external force applies. That's the first point. Second point, momentum is a vector. Again, of course we said this, but it's worth emphasizing, right? So momentum can be positive or negative, say with the truck and the car. Had we taken both velocities initially as positive, we wouldn't have gotten the wrong answer. And in fact, we would have, this would have been a different situation. We would have described a situation where the car and the truck are going in the same direction. Physically different answer. And the total momentum of a system can also be positive or negative. Again, it might be confusing. It might be like, oh, the system has a total momentum that is negative. That doesn't make any sense. Of course it makes sense. Right? It just means you've defined your coordinate system in such a way that there's more mass, in a sense, going one way rather than the other way. Maybe more in the direction that's opposite your axis. So in 2D and 3D problems, and we'll come to those, that means the fact that momentum is a vector means that it has magnitude and direction. So it is at an angle with a certain magnitude, or you can think about it in terms of components in x and y. And again, that's something despite the fact that having talked about in class, I see mistakes being made there all the time, where you just sort of take the overall speed times the mass, but no, you have to think about x velocities and y velocities. We'll talk about those, we'll do some examples there. Usually, momentum is used to figure out the before and after of a collision. Right? So by collision, I mean a violent interaction that lasts for that's called a short amount of time. Notice though, before and after here means right before and right after. Right? So right before the truck and the car crash, what are their respective momenta? Right after they've crashed, like a second later, what is the momentum of the car and what's the momentum of the truck? Those are the relevant quantities, not what happens half an hour later after they've been sitting next to a tree that they hit. Right? Of course, if you wait a little bit longer, other things are going to happen and things are slowing down or speeding up and so on. So right before, right after. So it's kind of saying, look, during the time interval, we can really ignore those other forces from the outside, the friction, the air resistance, in the case that we looked at. If we wait too long, well, then those will be relevant again, because it's probably the friction with the ground that will ultimately bring the two vehicles to rest. Now, final point, a collision in this context here means a time-limited interaction. It's the more formal way of saying it. It's some kind of interaction that lasts for a short amount of time. Of some kind during which the influence of forces external to the system, say the air resistance I just mentioned, those are irrelevant or just really non-existent. Another thing to note is that interaction doesn't mean that they must be physically bumping into each other. Right? So we can have other short-lived interactions and still call it a collision in the physicsy sense. Here's a good example that's maybe surprise you. Right? You have some distant comet or maybe a meteorite or whatever it is. It passes close to Earth. It doesn't hit Earth. It doesn't actually smash into Earth, but it gets gravitationally bent around it. Force of gravity acts on it, changes its path a bit, and then flies off again distant space in a different direction. That interaction, while the Earth and the comet, or the more likely comets don't really come close to Earth very often, but when we say meteorite, while they were sufficiently close that the gravitational force between them was relevant, was significant, well, that time interval we can call a collision, even though they didn't physically smash into each other. Keep this list handy as you're solving problems, and also maybe while we're talking about some more examples in the follow-up videos. They'll make more sense, and they'll hopefully help you avoid some of those mistakes that I see over and over and over when I see students tackle momentum problems. Alright, now you know about momentum, the rest is applications. I'll see you there.